Hi, this is the second lecture for Math 114, 1114. This is covering section 5.1 from the Briggs Calculus book, and this lecture is on approximating area under a curve. The first thing we're going to do is kind of talk about the big idea here. This topic that we're doing today, it's not easy, but it's the underlying core for everything that we're going to do for the rest of this course. It's also, the first half of 1152 is going to be based on this idea. So it's really important that you spend the time and make sure you really understand what's going on here today. So before we get into a bunch of notation and technical details, I want to just kind of talk to you about what it is overall we're trying to do. All right, so in 151, the big thing that you were trying to do was find the slope of a curve. And if you remember, we decided that that was the slope of the tangent line, and that was the same as the derivative. Now the big thing that you're trying to do in 152, which is now also 1114 and 1152, is to find the area under a curve. That's our big idea. So the first thing we need to ask ourselves is, what is area? And the easiest way to do that is it's the two-dimensional space something takes up. All right, so we're looking at for how much two-dimensional space. So we're going to measure it in squares. So if we look at kind of these pictures over here, what is the area of this yellow rectangle? Well, how many squares are inside there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. All right, so this is 18 square something or another, square units. All right, so you're looking at me going, there's a much easier way to do that. Absolutely. We can find that area by just multiplying, right? 3 this way, 6 that way, so 3 times 6 is going to give us 18. Now what about the triangle over here? We look at the triangle and we can count the squares inside of that. 1, 2, 3, 4, 5, 6. And then if we kind of match up these extra ones, 7 and 8. So we think here the answer is 8. We could also use the formula, right? Half base times height, which is just thinking of this as a whole big square and then taking half of it, right? But the counting thing isn't going to work so well when we go to look at the circle, because it takes up parts, right, of squares. Like right here, how much of the square is that? Or over here, a little tiny bit. So we could get a good estimate. We could count them. 1, 2, count how many are inside here. There's 16 in this big one. Plus, I don't know, maybe about 2 more on each of these sides. So 16 plus 8, we're going to guess it's like 24. To find the exact area, you could use the formula, pi r squared, which in this case would be pi, the radius, which is 3 squared, or 9 times 3.14. So our guess wasn't that bad. Okay, so how though do you come up with this formula, pi r squared? Or how do you find the area of a shape that's not one that you have a formula for? Well, we're going to develop a method today that's going to let us do that. So let's look at like a shape that's not quite so regular. This is the graph f of x equals x squared between 0 and 1. So here's 0 and here's 1. So we're looking at what's trapped under that graph between these two x values and the x-axis. And we want to find the area of that shape. So we could get a pretty good approximate just by counting squares like we did before. So if we put these two together, that's probably about 1 square. Here's another one. Here's another one. Maybe these two give us 1 square. That's 4. 5, and then a little bit. So let's just say it's about 5. And that's okay if you don't want to be exact. But we want, as a method that we can generalize, that it's going to give us the exact area. So the way we can do that, or at least before we get to exact area, we want a method that we can generalize for any curve. So just counting isn't really a method. But if we look at the squares underneath the curve in columns, then we can say, in this column, how much is under there? Well, we're saying it's about whatever this height is. And then in this column, we're going all the way up to here. This column, it's about 2 1/4. And this column is all of this. Now, this is obviously too much, right? If I count all these rectangles. But this is an algorithmic way that we can do it. We can always say, split your region up into rectangles, decide on one height to pick for your rectangle. So in this case, I'm always picking whatever's out farthest to the right. And then find the area of every rectangle and add them all together. And that should give you an approximation for the area under the curve. So what did I just say? I said, cut your area into rectangles, find height based on the curve for each rectangle. Find the area of each rectangle. And then add them all up. All right, so that's what we're going to be doing. That's the method that we're going to use. Okay, so in this particular case, if we're using x squared, we're going to find the heights. We're going to cut this area up into 4 pieces. So here's rectangle 1, rectangle 2, rectangle 3, and rectangle 4. And for rectangle 1, we're going to use the x value of 1/4. We're going to plug that into the curve, so that would be 1/4 squared, or 1/16. And we're going to use that for the height. Now for the second rectangle, we're going to plug in 1/2, this endpoint right here. And when we plug it in, we get 1/2 squared, which is 1/4. And then for the third rectangle, we'll plug in 3/4, so 3/4 squared is 9/16. And then for the fourth rectangle, we'll plug in 1, and 1 squared is 1. Okay, so there's the height of all the rectangles. If we want to find area, remember area is height times width. So we have the heights. How wide are these rectangles? Well, you can just kind of look here. Each width here is 1/4, right? Because we took 1 and split it into 4 pieces. So the width is 1/4. The way you would do that in general is you would say that if we're going from 0 up to 1, that's a length of 1. 1 minus 0 gives us a length of 1. And then we're going to divide it up into 4 pieces. So we get 1/4. All right, so rectangle 1, maybe we can go right here. The area of rectangle 1 is 1/16 times 1/4. The area of rectangle 2 is 1/4 times 1/4. The area of rectangle 3 is 9/16 times 1/4. And the area of rectangle 4 is 1 times 1/4. So if we add all those up, we're looking at, 1/64. And then it's 1/16, so that's 4/64. That's 9/64. And 1/4, which is 16/64. Adding them all together, we get 5 plus 9, 14, plus 16, 30/64. All right, so that is our approximate area. Now, how does that compare to, back here on this page, if we were just counting rectangles, it looks like there's 1, 2, 3, 4, 5, 6, and maybe 1/4, 7. It looks like there's maybe like 7.5 squares. So how does 7.5 match up with 30/64, or 15 30-seconds? That's closer to a half, right? Not 7.5. Well, this makes sense if you think about how big one of these squares is. this isn't a square of unit 1. This is a square that's a fourth on this side and a fourth on this side. So the area of one of these squares is actually a 16th. So you have 7 halves squares, where each square is size 1/16. So that's giving you, let's see, 7, 15, 30 seconds. Hey, that worked. Okay. So we've approximated area by actually computing out an example here. What do you think? Do you think that was a very good way of approximating the area? Can you think of a way to make it any better? One way that would make it better, if we could choose something other than just the endpoint, right? Maybe we could be smarter about how we chose the height. So if we picked the height, this point, the one in the middle or something, that might have been better. And we're going to talk about that in a little bit. But another way we can make this better is by using more rectangles. So let's look at this interactive figure here. Here's the shape we've been working with 4 rectangles, and it's getting an area of 0.469. But what if we use more rectangles? There's 7, 8, 9, 10, 11, 12, 13. Look at the shape that the rectangles are tracing out. It's getting closer and closer to the area that we actually want. So if we used enough rectangles, we should be able to come up with an answer that's really close. So here's 42 rectangles. That's my next slide. It says try this again with 42 rectangles. My goodness, that's a lot of rectangles. And at this point, if somebody says to do this with 42 rectangles, you probably want to look for a pattern. Or you're going to get your calculator out and you're going to be doing a lot of adding. So what's the pattern? Well, the width is pretty easy. It's always, if you start at 0 and you go up to 1, it's going to be 1 minus 0, length of 1, split up into 42 pieces. So the width of each rectangle is 1 over 42. But what about the height? Well, the height is going to depend on where you pick the x value. And then you're going to take that x value. So we're going to call these x values that we're plugging in, we're going to call those x bar. And we're going to put a little k under it. That says it's rectangle number k. And we want to, for our height, we're going to do f of x bar k. That's going to be the height of rectangle k. So in this case, since our function is x squared, it would be x bar k squared. And so that would mean the area for each rectangle would be 1/42 times x bar k squared. And as you can see, x bar k is going to be a different number for each rectangle. So we really can't go much farther than this, without pulling out a calculator and writing down 42 different numbers we want to add up, or getting out, coming up with a more mathematical notation, which is what we're going to do here in a minute. That's going to enable us to get here quicker. To give you an idea, though, what would this be like? Well, if we were going to do it with a calculator, we would have each rectangle would be adding up. So for rectangle 1, we'd have a width of 1 over 42 and a height of, well, let's see, x k bar k for the first one would actually be 1 over 42, so 1 over 42 squared, plus rectangle 2 would have 1 over 42 times, well, the second rectangle would be 2 over 42 squared. That would be the point you'd be plugging in, plus rectangle 3 would be moving over 3 widths, so that would be 3 over 42 is the point, as that's the x bar. And we square it to get the height, and then we get 1 over 42 again for the width. And we just keep doing this until we get to the very last rectangle. So rectangle number 42 would be a width of 1 over 42. And what are we plugging in for the last rectangle? Well, we've gotten all the way to the end, so we'd be plugging in 1. So you'd fill in these dots with all the missing ones and add them up with your calculator. And we could do the same thing even if we don't even know how many rectangles there are. If we just call that number n, we could say that, for the first we could say the width is going to be, we're going to take this interval from 0 to 1 and split it up into n pieces. So the width would be 1 over n. And the height, it's still going to be f of x bar for each rectangle. We're going to look at rectangle number k. So that would be x bar k squared. So for rectangle 1, we're looking at, the first point would be 1 over n squared with a width of 1 over n. Plus for rectangle 2, we'd be looking at 2 over n because we're going to have gone over to the second rectangle. So the second x value here, squared times 1 over n for the width. Plus rectangle 3 be 3 over n because we've moved over the width of 3 rectangles squared times 1 over n plus, and we can keep going until the last one would be 1 squared times 1 over n again. Okay. So hopefully that makes some sense, at least the big idea here. Let me summarize what we've just done. We've decided that, here I used I instead of k. But we decided that to find the area under the curve, we're going to split it up into rectangles. We're going to find the area of rectangle number k, the kth rectangle, by taking its height times its width. Then we're going to add all those together to get to the sum of all the rectangles. That's going to be approximately the area under the curve. And the more rectangles we have, the better it is. Sound reasonable? Okay. So now we need to start developing notation that's going to make this easier, less cumbersome to deal with. So the first thing we're going to do is learn about something called sigma notation. The sigma, that's the shape. It's the Greek letter S. And we're using it here to stand for sum. This is a notation for adding stuff up. So if we take this sum of all of these numbers, where these numbers are a1 plus a2 plus a3 all the way up to an minus 1 plus an. These dots mean we're, the stuff in the middle, right? So ai, this is called the general term, but you're going to think of this as your formula. And the I here, that's called your index, but you're going to think of it as your variable. And what this is saying is you let your index, I, start at whatever number is here at the bottom. So we're going to start at 1. And we're going to plug in every number between 1 and whatever's on top. So this is the number you end with. So a sub 1, that means we took the formula a sub I and we plugged in 1 for I. And whatever number we get, that's the first term. And then we move up by 1. We go from 1 to 2. We plug in 2 for I in our general term. And that gives us our second thing we're adding up. Then we plug in 3, 4, 5, 6, and we stop when we get to whatever number is on top of the sum. So let's try this. If it says I goes from 1 to 4 I goes from 4 to 9, I goes from 4 up to 9 of I squared. So this is our general term. We're going to start by plugging in 4, so we get 4 squared. Then plug in 5, because that's the next number, squared, plus 6 squared, plus 7 squared, plus 8 squared, plus 9 squared. And we stop at 9 because that's the number that's on top of the sum. And then you get your calculator out and you can add them all up and you'll get a number. All right. So that's sigma notation. Now this is helpful because, at least for certain sigma notations, there's actually a shortcut to finding the answer. So if you're just adding up a single number from 1 up to n, the shortcut is, if you're doing 1 plus 1 plus 1 plus, and there's n of them, well, how many do you have? You just have n. So that's the answer. The shortcut is just to get n. If you're adding up the numbers 1 plus 2 plus 3 plus 4 plus 5 plus 6, plus all the way up to n, then you're always going to get n times n plus 1 divided by 2. If you're adding up the numbers from 1 to n of I squared, you're always going to get n times n plus 1 times 2n plus 1 divided by 6. And if you're adding up the numbers from 1 to n of I cubed, you always get n times n plus 1 divided by 2, the whole quantity squared. So it looks just like I, only the whole answer is squared. So without adding anything up, you can tell what the sum of all these numbers is going to be. Let me show you an example. Let's add an example in here. So if we wanted to add up, I goes from 1 to 400 of I. That means we're adding up 1 plus 2 plus 3 plus 4 plus 399 plus 400. So that might take us a while if we get out our calculator to do it. But we can remember the formula, sum I goes from 1 to n of I is n times n plus 1 divided by 2. And so that means here n is 400, so 400 times 401 divided by 2. So whatever that number is, that's the same thing you're going to get if you add up all the numbers from 1 to 400. Sigma notation also has a couple of nice properties. If you are adding up a constant times your formula, you can take that constant out front. So you can add up all the numbers and then multiply by the constant. And this is just factoring out. You're just factoring out the c. And also if you're adding up, if you have two formulas inside here and you're adding or subtracting them, you can split them up and add up all the a terms first and then add up all the b terms and then add the sum together. You can break sigma notation over addition or subtraction. And this is just like putting in parentheses to add up stuff in a different order. Okay. So for an example, if we wanted to add up I goes from 1 to 20 of 3k cubed plus 6k, then we want to try to make these look like the sum of k cubed and the sum of k, because we know how to find those answers without adding anything up. And the way we do that is to first split it up over the addition sign. So we're going to get the sum I goes from 1 to 20 of 3k cubed plus the sum I goes from 1 to 20 of 6k. Right, and so then for each of those, we have a constant times a formula, so we can pull the constant out front. We get 3 times the sum I goes from 1 to 20 of k cubed plus 6 times the sum I goes from 1 to 20 of k. And now we've gotten exactly summations that we have formulas for. Note that they start at 1, they go up to some number n, and they're just k. Well, this isn't right. These should all be k's. They have to match. This is a typo. Whatever's here underneath, this is telling you what your variable is, has to match what's in the formula. So if you remember now, the formula for k cubed, we just pulled the 3 out front, was n, so 20, times n plus 1, 21, divided by 2, the whole quantity squared. Plus, now we pull down that 6, and we get 20 times 21, n times n plus 1 divided by 2 for the k. And so that's just a number now. You can calculate that out, and that's your answer. Okay, so that's sigma notation. You can see how that's going to be helpful with these areas because we're adding up a bunch of things, and they're a pattern to what they are. There's a pattern to what we're adding up, so we can write down what we're trying to add up in sigma notation. Now the next thing we need is kind of some general concepts of notation for these rectangles. So we're going to say, for example, let's look at a specific example again, and then we'll figure out the general notation. So this example, we're going to sine of x between 0 and pi, and with 6 rectangles. So you can see I've drawn that. Once again, I've used the rightmost point to determine my heights. So here's 0, here's pi. And everywhere where one of these rectangles meets the axis, those are all important points to me, including this beginning point, which we always call the beginning point A, and this ending point, which we call B. So all of those points are really going to be important, so we're going to give them a name. We're going to call them grid points. And you can see here that we've written down all the grid points for sine of x between 0 and pi. And in fact, the sine of x doesn't matter, right? What matters is we're splitting up between 0 and pi into 6 pieces. And that tells us what our grid points are. These are our x values that are going to be important. All right. How do you find them? Well, if you know how wide one of these rectangles is, then you start at A, you start at 0, and you move over the width of one rectangle. That tells you the first grid point. Then you move over the width of another rectangle. So if you add 2 delta x's, 2 widths, you're going to get the second grid point. If you add 3, you're going to get the third grid point. So in general, what we're saying is you start at A, you end at B, you have all these grid points in between. We're going to call them x0 is A, then x1 is the first grid point, the next 2, the next 3. Does this make sense? And the width between them, we're going to call that width delta x. That's the notation for width. It's how much x changes as you move from one rectangle to the next. And we can always find delta x the same way. We can find out how far it is from A to B. So the length from A to B is B minus A. And then we split it up into the number of rectangles we have. So if we have n rectangles, we'll split it up into n pieces. So delta x, the width, is always b minus a divided by n. And once you know that number, you can find x sub 1, because it's always going to be your a value plus 1 delta x. You've moved over 1. You can find x sub 2, because it's always going to be your a value plus 2 delta x's. You've moved over by 2. X sub 3 is always going to be a plus 1, 2, 3 delta x's. And so on. You can see the pattern. So x sub k, so rectangle number k, is always a plus k times delta x. So you can write out what all the grid points are using this formula. This is the grid point formula. And when you do this, when you split an interval up into these grid points and they're all equally spaced, we call that a regular partition. That's a vocabulary word for you. So we've learned about grid points and we've learned about a regular partition. All right, so in this particular example with sine, can we find the width? Well, the width should be b minus a over n. So the starting point in this picture is 0, so that's our a. And our ending point is pi over 2. So we have pi over 2 minus 0 divided by how many rectangles we have. So we have 6 rectangles, that's our n. So we have pi over 2 minus 0 divided by 6, or pi over 12. And that should make sense because our first grid point is at pi over 12. We've moved from 0, a distance of pi over 12, to get to pi over 12. Okay. So now we have grid points, we have width. The other thing we need for area is height, because if we have width and height, we can find area. So far we've been finding height by plugging in the rightmost point at the bottom of each rectangle. In general, you could use any point on the bottom of the rectangle. But so far for rectangle 1, we've been using grid point x1. For rectangle 2, we've been using grid point x2, and so on. Like I said, though, you could actually use any point inside that rectangle. So if we're looking at this nice highlighted rectangle here in the center. It has a width of delta x, and they're using this point here, x bar k, because this is rectangle number k, to find the height. So they plug in this x value on the x-axis into the function, and they get this height on the curve. So then they draw in the rectangle having that height. So you can see from these different examples here, x1 bar, x2 bar is kind of in the middle, k bar is a little bit to the left. You can actually pick any kind of point in there, and that would give you some kind of rectangle approximation of that area. So that's what we call a general Riemann sum. Well, or at least a Riemann sum. Let's cross out the word general. That we can be even more general than this. But this is a Riemann sum where you pick any point. Let's call it. We're going to put a bar on it over it. That means that's the one you plugged in. And inside that, the bottom of rectangle 1, inside that first interval, you pick any point you want, and that's how high you make that rectangle. And then you could do it again for the next one, and again for the next one, and that's called a Riemann sum. All right, so there's specific Riemann sums we actually use a lot. The one that I keep giving as an example is the right Riemann sum. That means for x bar k, so for rectangle number k, the point you're going to plug in is the same as x sub k, which is the grid point. So the point you plug in for height is the grid point. And that's called a right Riemann sum because you end up plugging in the rightmost point at the bottom of each rectangle. So rectangle 1, you're plugging in the rightmost point there. So we could say that we could come up with an entire formula for the right Riemann sum. So for rectangle K, it's going to have a width of b minus a over n. We already said that. And it's going to have a height of f of x bar k. It always has that height. But in this case, it's f of xk, because we're saying the grid points, it's a right Riemann sum, so the grid points are the same as the points you're plugging in. And we actually have a formula for the grid points, right? Remember we said x sub k is a plus k delta x. So our height is f of a plus k delta x. So the area for rectangle K is the height, f of a, plus k delta x, times the width, which is just delta x. And now we get to use our sigma notation to say that the area of the entire shape is approximately the sum starting at rectangle 1 ending at rectangle n of the area of each of these rectangles, so of f of a plus k delta x times delta x. So this right here is your formula for a right Riemann sum. So that's important. You'll want to remember that. Now we could also do a left Riemann sum, and that would mean that we would take the leftmost point for each rectangle. So for rectangle, this is rectangle 1, see it has a height of 0. Rectangle 2 has a height of whatever you get when you plug pi over 12 into sine. And here's rectangle 3, now we're using the leftmost point to find the height. This is called a left Riemann sum. And the difference here is for rectangle number k, the point you plug in is actually the grid point before k. So let's see if this makes sense. For rectangle 1, the point we're plugging in is actually the grid point. Remember, this was x sub 0, 0. And then for rectangle 2, the point we're plugging in is actually x sub 1. Does that make sense? So our formula is going to be the same as before. It's going to look like a sum from k goes from 1 to n of a height, f with something x bar k, there's your height, times delta x, there's your width. But this time, the x bar k is actually the grid point xk minus 1. So that's actually going to be a plus k minus 1 delta x. So our formula for the left endpoints is k goes from 1 to n, f of a plus k minus 1 delta x times delta x. There's your formula. And now a third way that we sometimes find Riemann sums is called the midpoint Riemann sum. And this is maybe the one that would make the most intuitive sense to you. You pick the point exactly in the middle of each rectangle, and that's the one you use to find the height. So in this case, the bar, the point you're plugging in, the midpoint, is the point exactly in between. So this is rectangle K. Now here is x sub k minus 1. Here is x sub k. And how do you find the point exactly in between them? We have to take their average. So it's x sub k minus 1 plus x sub k divided by 2. It's the average of those points. The other way you could think of it is you could think of it as starting at x sub k minus 1 and adding on half of a delta x. In either case, that's going to give you this number right here. So our midpoint formula, it's still a sum, k goes from 1 to n, of a height of x sub k bar times delta x. But this time, x bar k, we just said, was the average of x k minus 1 and xk divided by 2. So our formula is k equals 1 to n f of xk minus 1 plus xk divided by 2 delta x. So we need to plug in, we need to simplify this, right? So if we simplify that, xk minus 1 plus xk divided by 2, that's a plus k delta x. That's xk, oops, no, that's xk. xk minus 1 is a plus k minus 1 delta x plus a plus k delta x divided by 2. And we can simplify that a little bit. That's 2a plus 2k minus 1 delta x over 2, or a plus k minus a half delta x. So there's your formula actually. That's your x k bar, the point you're going to be plugging in for the midpoints. And so your final midpoint formula is the sum k goes from 1 to n of f of a plus k minus a half delta x times delta x. So those are your three formulas you want to remember: the midpoint, the left, and the right Riemann sums. So now how about we actually use one of those formulas and plug in some numbers in, because I know it's really confusing when there's all these letters and variables. So let's try an actual example, and then we'll quit for the day. So this is just a summary of what we said. We have a Riemann sum. That's where you can pick any points you want to plug in, any points for the x bars. But usually when we're actually calculating, we'll either do a left or a right or a midpoint. So let's look at an example. Let's go back to, let's actually do this. F of x equals sine x from 0 to pi over 2. And let's write down the right Riemann sum, the left Riemann sum, and the midpoint Riemann sum. So the right Riemann sum is going to be the sum, k goes from 1 to n, of f of a plus k delta x times delta x. Now it doesn't matter which of these sums we're doing, delta x is always the same. So we can find it. Delta x, we already found it for this one, right? It was pi over 2 minus 0 over 6, because we're using 6 rectangles. So that was pi over 12. All right, so that means that for the right Riemann sum, we've got k going from 1 to n, f of, well, a, here is 0. So 0 plus k times pi over 12. So that's your xk bar right here, the 0 plus k pi over 12. And then just your width outside of that. So the width is pi over 12. And then the last thing we need to do is actually plug in the point to our function. So the final answer is going to look like the sum, k goes from 1 to n, of sine, because that's our function, of k pi over 12 times a pi over 12 here outside of the sine. So there's your right Riemann sum. The left one is very similar, except the formula is just slightly different, right? It's f of a plus k minus 1 delta x times delta x. So it's going to be the sum, k goes from 1 to n, of sine of 0 plus k minus 1 times pi over 2. And then a pi over 12. And then a pi over 12 on the outside for the width. And then the midpoint, once again, looks exactly the same, except for we have sine of 0 plus k minus a half times pi over 12 times pi over 12. So we've applied this formula that we've come up with to the specific function of sine of x between 0 and pi over 2 with 6 rectangles. And if we unpack what it says, let's just do one of them. Let's look at the right Riemann sum. You can see why people we like to use the right Riemann sum best, because the formula is the simplest. Just slightly simpler, but it is still simpler. So if we're looking at the sum, k goes from 1 to 6. Oh yeah, I kept saying n here, but we know n, right? n is 6. We have 6 rectangles. Okay, so if we have the sum, k goes from 1 to 6, of sine of k pi over 12 times pi over 12. How would you actually calculate that? Well, the easiest way, really the only way that we know, is to actually write out what it means. So first we're going to start with k being 1, and we plug that in. So we have sine of 1 times pi over 12 times pi over 12. That's the area of rectangle number 1, plus what comes after 1? 2. So sine of 2 times pi over 12. And then the pi over 12 for the width. So that's the area of rectangle 2, plus sine of 3 times pi over 12 times pi over 12. That's the area of rectangle number 3, plus sine of 4 pi over 12 times pi over 12. That's area of rectangle 4, plus sine of 5 pi over 12 times pi over 12. That's area of rectangle number 5, plus sine of 6 pi over 12 times pi over 12, and that's the area of rectangle number 6. So those are numbers, you add them all up, and that gives you that approximate area that we're looking for. Notice that when we wrote all these things out, the only thing that was changing was the number that got plugged in where the k was in the formula. And we're just plugging in all the counting numbers starting at 1 and ending at 6. Just like we said, that's what the sigma notation does. Everything else we're just copying is exactly the same. All right, so we're going to stop for today. I know that was a lot. We'll talk about it a little bit more for the next lesson, and we'll talk about how we can turn this into an exact area by using as many rectangles as we possibly can. What's the biggest number of rectangles we could use? We could use infinity. So that's what we're going to do next time. We're going to talk about using infinite number of rectangles. So all that limit stuff that you may have forgotten, you're going to want to remember. So you might want to review limits to infinity before you watch the next lesson. All right, thank you very much. Have a good day.